When you flip a coin, the moment it lands, all uncertainty vanishes. It is absolutely heads or absolutely tails. Our everyday computers operate with that same certainty. Every photo, text message, and website is built on a flat, rigid binary chain of ones and zeros. A 1 is heads, a 0 is tails. But picture that same coin while it is still spinning in the air. Before it hits the table, it holds the potential to be either outcome. In physics, we call this wobbly in-between blur a superposition. Modern processors struggle to calculate using a blur. To force a computer to hold on to that delicate spinning state, researchers typically rely on million-dollar laboratories, cooling highly specialized hardware to near absolute zero. Making quantum-style math possible on a desktop machine requires a new approach. This handwritten proposal suggests we can record that spinning state by mapping the path of the wobble as it happens. Moving past the cooling barrier isn't about better hardware. We just have to change the mathematical language we use to talk to the computer. A researcher named Rupesh Malpani developed a framework called QxBin to solve this translation problem. The goal is a personal qubit simulation. QxBin breaks the traditional flat line of ones and zeros into a two-dimensional grid. Think of this probability matrix as a digital punch card. To capture the spinning coin, the framework replaces whole numbers with fractions. If the coin leans, the coordinate records 3/4 heads. These handwritten equations show the specific notation the framework uses for these fractions, placing the ratio of 1 to 0, written here as I/O, across the grid. By using these simple ratios instead of strict whole numbers, a standard computer suddenly has a way to process uncertainty. A spinning coin doesn't just lean, the intensity of its wobble constantly changes. We need to record how heavy that lean is across our grid. By raising our fractions to different positive and negative powers, the math scales the weight of the probability up or down. This creates a precise set of mathematical coordinates, showing exactly what the superposition looks like across the matrix. This page from the formal proof displays the equation for an individual grid entry, combining a global constant with our exponents to ensure the probabilities always balance out perfectly. We have the math, but how do we get the physical action of our coin into a regular computer without using highly sensitive lab equipment? Modern magnetic keyboards provide a surprisingly effective solution. They use Hall effect sensors. A typical keyboard only registers a binary click. A Hall effect sensor measures the exact magnetic depth of your keystroke as you press it down. The computer reads that depth as a percentage. If you press a key halfway, the sensor captures a 50-50 split, supplying the exact fractional ratio the grid needs to calculate the state of the spin. This data shows real-world testing results, comparing the QxBin grid against professional quantum software. The numbers match, proving that a classical machine can accurately process a simulated qubit. There are no freezing temperatures or massive power requirements here. It runs entirely on room temperature mathematics. Standard binary code is designed to store finished results. QxBin provides a language designed to track the process of the coin while it is still in the air. This puts these advanced tools in the hands of any student or developer with a standard laptop. You can start experimenting with quantum logic today. The entire process comes down to one specific swap, leaving behind a rigid line of ones and zeros for a spatial map of fractional probabilities. Pushing computing forward doesn't always require building a bigger machine. Sometimes we just need to change the math we use to measure the spin.